we said that the speed of light in empty space, the speed of light in vacuum, we can calculate it that way. We're not always in vacuum. Sometimes we're sending light through air or water or plastic, like in the lab. Okay, so we're not always talking about the permeability and permittivity of free space. The speed with which electromagnetic waves, light, travel in some medium is it's the same expression, just we sub in the permeability and permittivity of the medium. The permeability doesn't really change very much unless we're talking about something ferrous, especially ferromagnetic. If we're talking about something ferromagnetic, it's not usually transparent, at least not to visible light. So we can't see through it, in other words. So it's very hard for us to visualize electromagnetic waves passing through this thing, traveling in this thing, because it looks opaque to us. We can still calculate it. For most things that are to us transparent, plastic, water, air, it's the permittivity that is the story. We don't unpack this too much. We just keep track of the fact that the speed with which light travels in a particular medium is generally different from the speed with which it travels in a vacuum. C, the speed of light in a vacuum, divided by V, the speed in this medium. Now, we borrow from Einstein, and we say that the speed of light is the cosmic constant. Everyone agrees. Whenever they look at light, they agree on the speed of light. So, and that's the fastest thing that exists. That's the deal. Everyone agrees, and that's the limit. So, I mean, because you think about it, permeability basically the same, but the permittivity goes way up the more stuff you put in the way. So dividing by a bigger number, I expect the velocity in the medium to be smaller generally than the velocity in a vacuum. And in fact, yeah, this is always a number greater than 1, unless we're talking about a vacuum, in which case it is 1. But we define this to be n. How much n is doing the job of saying how many times faster is light in a vacuum than in this medium. It's a way of keeping track of how fast light travels in this medium. A way of keeping track, like an index. An index of what? Well, it's a speed index, actually. But it turns out to be the index that keeps track of the behavior of light called refraction. This is different from reflection. This is propagation through different media, as opposed to hitting a boundary and bouncing off. This is hitting a boundary and keeping going in a particular way, and that's refraction. The indices of refraction of various materials are in our textbook. There's a table. If you need one, I'll be able to provide it to you, or it'll be the thing that you're asked to calculate based on the other information. Suppose there's a boundary between two media, air and water. Makes sense. It's nice we have some intuition for that. Sure. For now, I'm just going to call them medium 1 and medium 2. Suppose we have, generally speaking, some parallel rays of light incident on this medium, on the boundary between the media. So we've got rays of light all coming parallel to each other. They're all hitting the boundary between the two media at the same angle of incidence. If we draw the normal at each point, each of these angles is the same. Now, suppose the other thing we know about media 1 and 2 is that light travels faster in medium 1. Okay, so if light travels faster, that means it has a lesser index of refraction. So in this case, N1 is less than N2. The difference between the speed of light in a vacuum and the speed of light in the medium is larger for medium 2. Now, if we replace N with what we know that it's equal to, that's C over V1, C over V2. This is the same C, so we can cancel that. And we can cross multiply. V2 is less than V1, which is what we said. The light travels faster in medium 1. But this is the speed, the propagation speed of an electromagnetic wave. So we know it's related to the frequency and the wavelength. Now, on the incoming ray has oscillating electric and magnetic fields. With a wavelength according to the frequency. So whatever the frequency is in medium 1, lambda is related to that. Suppose we asked for all the points on this ray that are crests, maxima of the sinusoidal function that represents the electric field, say. Let's say there's one here, and one here, and they're all equally spaced. And the spacing between them is lambda. Lambda 1 in this case. But if all of these rays basically came from the same source, then they're all lining up. All of their crests happened at the same time. So if we connect all the points that have maxima at the same time, we end up with parallel lines perpendicular to the rays that represent the direction the light is traveling. These are collections of points that are all in phase. They all have maxima at the same time. These things are called wave fronts. And the distance between each wave front, from here to here, that's lambda 1. Now, this point here, right at the boundary, this wavefront is saying, hey, right there, be a maximum. Because that's what the wavefront says. You got a crest right there. Just on the other side of the boundary, the particle there, it needs to be a maximum because that, like, the particle that is the boundary can't do two things at once. If this wavefront says you got a crest, it's okay, I need to have a maximum. I can't do anything about that. This point on the boundary is going to have maxima every so often. And then the particle of the medium just inside is right next to that particle on the boundary. And it keeps seeing its neighbor do the same thing every so often. And it says, okay, I do the same thing every so often. The every so often part, that's the frequency. We can't have different frequencies on one side and the other. Because then we've got a particle at the boundary trying to do things at, like, trying to simultaneously do two different rates. It's like if I said, okay, jump up and down. And then while you're doing that, also jump up and down twice as fast. It's not a thing we can do. The frequency needs to be the same across the boundary. This is called continuity. Things have to line up from one side to the other. So we don't need these subscripts, which means that's the same frequency f. So we can cancel that. And that means that lambda 2 has to be smaller than lambda 1. But at the boundary, we need to have maximum where we're supposed to, because we can't tell this point on the boundary to do two different things. If there's a maximum here, okay, there's got to be a maximum there. So tracking the maxima in medium 2, we draw wavefronts. The wavefronts, whatever we draw, have to hit those points. But they can't be the same distance apart from each other as these lines, because lambda 2 has to be less. The only way to do that the only way to satisfy all these considerations is to have the wavefronts bent. Now, if we draw lines of propagation perpendicular to the wavefronts, just like these, perpendicular to the wavefronts, and we draw the normal for those directions of propagation. These angles are all the same, but they're smaller than these angles. Use the same symbol, theta r. We're not talking about reflection anymore. We're talking about refraction. These thetas are related by geometry. With a little bit of work, we can prove the following. If you're curious about the proof, it needs no calculus. It is just geometry. We can do it, well, a little bit faster than that, or a little bit slower than that. But we can show. If we remove the i's and r's and just call them 1 and 2, okay. Theta 1, the angle of incidence, the angle with respect to the normal of the incoming direction of propagation in medium 1, and the angles in medium 2 measured with respect to the normal. I don't know why we call this Snell's law. It's just geometry. It's just an expression of continuity at the boundary. We could call it the refractive continuity law, and it would be just as meaningful. I guess it's Snell that did it first. We could prove it just as well. Cool. This is great. If we're going from a fast medium to a slow medium, like is pictured here, everything's fine, no problem. What if we're going the other way? What if we're coming up in water, going to air? Should still be fine, right? Well, let's find out. Here we are in medium 2. I want to solve for theta 1, the angle at which we leave the boundary, the angle at which we leave the normal in the new medium, medium 1 in this case. Okay. So sine theta 1 is n2 sine theta 2 over n1. Ask for theta, we need the inverse sine of n2 over n1 sine theta 2. Now, this is fine, except the inverse sine function can't handle any arguments larger than 1. There is no angle whose sine is larger than 1. If we happen to come at this boundary with a theta 2 large enough that when we multiply by the ratio between the indices of refraction, We end up with a number here that's bigger than 1. No such thing. It cannot refract through. It can't, doesn't happen. There's no way to satisfy this relationship, which just comes from geometry. There's no way to do it, so we can't. And it has to get reflected away from the boundary, and that's what we saw in part B of the Snell's Law Labs, total internal reflection. If we're talking about plastic, we never make it out of the plastic into the air. We just hit the plastic boundary and come back. What is the critical angle at which we can come at the boundary and just like skim along the surface? Well, it's the angle that makes this equal to 1. Sine inverse of 1, technically that exists. It's 90 degrees. 90 degrees to the normal. Normal points up, 90 degrees to that, where you just kind of skim along the surface. When you watch the video for the experiment, think about that color dispersion right at the edge and that like last little glimmer of red light that skims along the edge of the plastic and then disappears. We're right there at the edge of theta critical. Total internal reflection. Theta critical is the angle that makes this equal to 1. All right, so N2 over N1 sine theta 2 equals 1. Okay, so we multiply N1, divide by N2, take the arc sine, theta critical is the arc sine N1 over N2. If we're going from the one into the other, there's no problem. Because we're not solving for theta 1, we're solving for theta 2, which switches this around. That's always going to be less than 1, we're fine. It's only when we're going the other way. From a generally denser medium into a less dense. From a more refractive, larger N, to less refractive, smaller N. Okay, next segment.